Should I start? Okay, so maybe for those who were online yesterday and didn't attend the exercise session, I was a bit sloppy yesterday in the first lesson with summing over the edges, where sometimes I was, without saying it, summing only over directed edges, and sometimes over both directions of the edges. And so some factor 2's that came up were not supposed to be there. So I discussed this in the exercise session. I will also, we can copy my notes, my handwritten notes, so that you will have, everything is still holds. The factor 2's were mostly in the proofs where we were showing that everything was equal to 0, so it doesn't affect anything. So now I will be more cautious about keeping track of when rho is over directed edges, then I will say rho positive, and when rho is undirected. Okay, and as I said, I promised to go to the physics, but there's one last thing I would like to do before going to the physics, is to introduce the concepts of cycles, because I will need it. So we had the incidence matrix, which, remember, the incidence matrix maps edges into nodes. And the cycles are the right null vectors of the incidence matrix. So in matrix form, it's this. And explicitly, it's the sum over the edges. Yeah, it's wrong in my notes. So I can give you an example because historically it was important. Schnackenberg, who's one of the one of the early formulation of stochastic thermodynamics without looking into fluctuations, but at averages, was done in '76 by Schnackenberg, and he formulated everything in terms of cycles. So let's take an example. Also, it's going to be an example of how to construct the incidence matrix, and I think it's useful to do it once. So I will call this edge 2, this edge 1, C, D, like this. This edge is 3, 4, 5. And I choose this orientation here. And now let's construct this incidence matrix. So we need to map edges. So edges is 1, 2, 3, 4, 5 into nodes A, B, C, D. Okay? So let's look at the first edge. The first edge leaves node A and enters node B. So it's -1, 1, and it doesn't touch the other nodes. Let's do edge 2. Edge 2 does exactly the same thing, -1, 1, 0, 0. Edge 3 leaves B and enters C. So it leaves B and it enters C. 4 leaves C, enters D. And 5 leaves B, enters D. Okay, so this is the incidence matrix of that graph. And there's a construction, I mean, this is more, we will not use it explicitly, but it's worth mentioning. To find these, so C are actually the vectors spanning the null space of the incidence matrix. And there's a graphical way to find those cycles, which is you need to pick a spanning tree. So a spanning tree is simply, you need to connect all the nodes without creating any cycles. So this is, for instance, one spanning tree. There could be other. And I put dotted line for the edges that I removed to get my spanning tree. Okay? And those edges that I removed, they define chords. They're called chords. And each chord defines a cycle. Let me put the orientation also here. So each chord defines a cycle, because you see if I add that chord, I create a cycle, this cycle in this direction, and this chord here creates a cycle in this direction. Okay? So these are two cycles, and now cycles, they map edges. So here in this case, I will have two alphas. So I can write C for alpha 1 and alpha 2, if this is 1 and this one is 1 and this one is 2. And I will now put the edges in the direction. So it's going to be +1, -1 for 2. So 1, -1. So these are the edges. 1, 2, 3, 4, 5. 0, 0, 0. And the other one, it's going to be 5 and -4, -3. Yes. Okay, let me do it bigger. Okay, so this is my spanning tree. I have all nodes, but no cycle. And if I add this chord, I get a cycle. This is going to be my first cycle, number 1. If I add this chord, I get cycle 2. And the direction is given by the direction of the chord. So I need to keep the original. And 5. So this is cycle. So this cycle rotates in this direction. Maybe numbering cycles with 1 and 2 was not the best idea, but let's go this alpha 1, alpha 2, alpha 1. And 3, 2, 1. Okay?
So by function, these cycles are counted?
They have the direction of the chord. So that's what gives the direction to the little arrow that I drew.
So first you wrote the tree, and then you found the possible cycles you can make. And
Yeah, because actually whatever edges I left out from the tree will create a cycle. And this is what are called chords. And each of these chords, if I now put it back, creates a cycle. Okay? So that's a graphical way of constructing those cycles. And you can check that if you apply D over C, you can try for each of them. I did it yesterday evening and it worked. So it should work for you too.
if you started from a different tree?
I could do the same and it will also work.
It will give the same cycle?
No, it will give other cycles. But I have freedom, right, because I have a basis. The cycle space cycles are vector that form a basis for the null space of D. But I have freedom of how to choose my basis. So that freedom is there, right? It's
so
like
the independent cycles.
Exactly. Yeah. Yeah, they are independent.
This works for whatever direction you choose for your cycle?
Yes. You can try it. Okay, this was actually a side note, but why it is important why these cycle play a role in stochastic thermodynamics? It's because you remember that a steady state was defined I said I would be cautious with the summation, and then I realized I'm still not cautious. This was rho positive, yes. I will do it, otherwise I will forget. Here we go. So this is over positive edges. So this was the definition of the steady state. You remember? Because this was the derivative of P. And so steady state is when the flux is evaluated at the P such that that derivative of P doesn't change. So steady state fluxes are in the kernel of D. So I can actually use the cycle as a basis to represent my steady state fluxes. Okay? And so if I do a decomposition, so this lives in the null space of D, and I can decompose the steady state flux as a sum over alpha. J alpha are the coefficients, C alpha E. And now let's go to the steady state entropy production. The derivative of the Shannon entropy is 0. So I have this summation over E. And this one, I will check because now I start having that. But yes, this one is with J. I'm breaking my rules. This is again positive. So before giving you my notes, I will check them once again. So we had this, and if I use now this decomposition for at steady state, okay, this is now at steady state, so the Shannon entropy doesn't enter because the derivative of the Shannon entropy at steady state is 0. I can rewrite this as a sum over the positive edges of the sum over alpha, J alpha, C alpha E, log W E, W minus E. And if I invert these sums, I get a sum over alpha of what I can now call G alpha is, I can interpret that as a flux along the cycle, multiplying what is called the cycle affinity. And the cycle affinity is the sum over every edge of C alpha log W E W minus E. So basically this affinity of the cycle is you multiply the log of the ratio of the rates along the cycle. Okay? And this, we know, must be always greater or equal to 0. So this is Schnackenberg. It's a review of modern physics, 76, where this E shows that the entropy production can be simplified like that. You can view it as a simplification compared to the expression, the original expression where we had to sum over every edge. He pointed out, look, at the end, at steady state, the only thing that contributes to dissipation are the fluxes along the cycles. And there's an affinity associated to that, which is given by these log ratios of the rates along the cycles. In a sense, what I'm going to show you today goes adding the physics, is also an attempt, well, is a way to go beyond that, because these cycle affinities, if you look at actual system, this was our motivation at the beginning, you realize that many affinities for a given physical system end up many cycles end up having the same affinity, which means that this decomposition is can be reduced into lesser fluxes, because if affinities are the same or linear combination of each other, you can express this as a sum over less currents. And this is going to be the topic of today. But I wanted to mention this because historically it was important, and because I will need the cycles. Good. Now we finally come to the physics. I will maybe erase to have a fresh blackboards, because I only need this. Okay, physics. Now, yeah. Yes. So it's the log ratio of the forward divided by the backward rate, but over every edge of the cycle. So it's like I take the log of forward divided by backward along this, plus the sum of the forward and backward, log of the forward and backward log. And this is what is going to give me this thing.
So if it's a equilibrium system, it's 0 for every loop, right?
Yes, because every current being 0, also the currents along the cycles will be 0. And also, also, yes, indeed. At equilibrium, all the affinities are 0. Okay, physics, and this will answer. Yesterday I had many questions during the exercise that were already trying to, that were asking, what about these edges that we introduced? Where do they come from? They're artificial in the mathematical description. And I said yes. So now we will see why I introduced those edges. And it's motivated by physics and the key notion of local detail balance, which is really the link between the math and the physics that allows that is at the core of stochastic thermodynamics. So now, we had edges, and we only had edges. So nodes and edges. And some of these nodes were connected by more than one edge. And what I introduce now are reservoirs. So let's use rho for the labels of the reservoirs. So this could be rho equal 1, rho equal 2, rho equal 3. This is a picture, of course. In practice, they will only enter via the rates. And then I use K, or kappa, but my kappas looks like K, so we can say K, which are conserved quantities. Okay, in what sense? Conserved quantities, let me give you right away examples. The amount of that quantity will be called Y, but K could be, for instance, one example of K could be the energy. Another example could be the number of particles, could also be the charge. So these are conserved quantities in the sense that we know in physics that they are conserved. And so they will lead to balance equation in the sense that if these quantities change when a transition happens in the system, the corresponding change must happen in the reservoir. Okay? But it is going to be quite natural because we know if energy changes here, it had to come from the reservoirs. That's the idea. If the number of particles changes in jumping from here to here, it had to come from the reservoirs. Now I assign to every node Y, K, and I have the index I because for every node I will assign Y, K to it. So this could be, again, energy inside, so example, energy inside I, or number of particles inside I. And I also assign an entropy, an internal entropy, to those sites. Okay? So I use the label K just because this could be a vector, like here. So this is the list of the amount of conserved quantity on that site. And I have, to each site, I assign an entropy and a set of conserved quantities. And to the reservoir, I assign intensive fields. So these are Fy. So let's say K, rho and K. And I will, for short, call these Y. So these are intensive field associated to the conserved quantities. So what is the typical field associated to energy? So let me write. It's 1 over T. For N, it's minus mu over T. For Q, it's going to be minus V, the electrical potential over T, etc. Okay, so this comes from thermodynamics. I can, you can see already that the product of E times F will have to do with the entropy, because if you write the differential of the entropy, it's ds is equal dE over T minus mu dN over T. So that's where this comes from. But for now, I introduce this intensive field. So for instance, I said y is rho and k. So rho here is 1. So for instance, if I assign F for reservoir 1 and energy would be 1 over T1. F for reservoir 1 and particle number would be minus mu over T1, mu 1 over T1. And same thing here, same thing here. So F 2E 1 over T2, F2N minus mu 2 over T2. And since conserved quantity are by definition conserved, they obey a balance equation, meaning that if I have a transition along an edge of a certain, the quantity, the conserved quantity along that edge, it's change. So the change along the edge is going to be this minus this. Okay, let's imagine, for instance, that we are here. We go from origin of edge to origin of minus edge via this edge E. So the change of the quantity y along that edge, so I have y here, the way in which it changes, this I can simply rewrite. This is by definition of the incidence matrix y k I d I e. So I sum over all the edges that are going to be selected as target or origin of the edge I picked, and I sum the transition. So this is only rewriting this in terms of the incidence matrix. But this now I will split. This is the important part. I will introduce yet another object, which is the sum over all the reservoirs of x. X depends on y, so it's an index of rho and k and e. So this is now how much of that quantity that changed when I move from here to here is exchanged with the different reservoirs. So the picture to have in mind is the following. I jump from here to here, and for instance, let's pick energy. The energy change between here and here is the energy here minus the energy here. This is this. And let's imagine that I took certain amount of energy from here and another amount of energy from here. So the change of energy here has to be equal to the amount of energy I took from this reservoir plus the amount of energy I took from this reservoir. This is what this equation is telling me. Okay? It's an abstract. There's a lot of notation, but the ideas are pretty simple. And I can do now the same for number of particles. I have what is the change of number of particles when I go along this edge? So it's the number of particles here minus the number of particles here. And this change must be the sum of the amount, that change of particle needs to be the sum of all the change of particle I got from the different reservoirs. Why? Because those quantities are conserved. Good. Now I missed the key point.
I'm sorry. So in the notation for X, so the amount of quantity that is exchanged with the reservoirs is dependent only on the number of the reservoir, on the K, so the type of the conserved quantity, and on E, so the type of number.
Yeah, you see, I have K, so if the number of K's balance equation. So for each K, I have a balance equation. So I would have one for energy, one for number of particles. So For each k, I have a balance. So this is a balance equation for a given k, and the change of that quantity yk along the edge is the change of that quantity k exchanged with every reservoir.
Yes, and the amount of this exchange depends only on the type of node that connects to
Yeah, because I assign to every node a conserved quantity and an entropy. And this is where I'm kind of implicitly assuming that my nodes, the nodes inside, the structure inside the node is an equilibrium, because I can assign an entropy to it, okay? And the reservoirs are also, of course, at equilibrium. But that's the physical picture. Now, how do we connect this to the theory of, yes? Well, because imagine that this would be a coarse-grained description where I lumped every node is a state of a human being. Or, yeah, but this is my point. This node need not to be out of equilibrium. Otherwise, I would not know what entropy to assign to it. Not temperature, only entropy. Some examples where maybe it's too strong even to say equilibrium. One typical example is if you have a mean field description of some Potts models. When you work at the level of density, you know that for each density, there are many microscopic configurations corresponding to that density. And the entropy you're going to assign to that state is going to be the number, the complexion number of microscopic configuration corresponding to that mesostate. So in that sense, I need to be able to assign an entropy. I mean, in many applications, it's actually too strong. I cannot say this. In chemistry, for instance, S plays a very important role, because if I'm dealing with a molecule in solution, the molecule has an internal entropy, and I need to account for that. So I will describe reactions will create changes between my molecules, but to each molecules, I need to be able to assign an energy or an enthalpy and an entropy. So that's an example where my node really needs to be at equilibrium. Molecule in solution is at equilibrium. The non-equilibriumness is in the transitions between the different states. For Potts, I also have an entropy, but there are many models like quantum dots where you don't need to care about the entropy. There's simply no entropy assigned to an electron in a quantum level.
So that basically at each node, there are these extensive variables.
Exactly.
And so you can define a corresponding entropy function.
Exactly.
Or those
Exactly.
with those
Yeah.
molecular,
Yeah. Exactly.
But then I can also define the local temperature in the same way you define the temperature.
Yes. The situation would be this there. So for Potts, for instance, you can use different. You have an entropy that comes from the complexion number. You can you define a local temperature for that? In most applications that I have in mind, when you have an entropy here to which you can assign a temperature, the system is isothermal, like chemistry. In most applications with non-isothermal, where the baths are at different temperatures, the entropy either is not there or is of a Potts model type, which is of complexion number. I don't have an example, so this is why I don't have an immediate answer of a system where I could assign a local temperature. But I don't, okay, it's not I will think a bit about it. But for the moment, I don't need that. You know, I simply need to say that I can assign an entropy and extensive quantity to the node. Yeah. Yeah, I will think about this. Now, where this is kind of still no connection with stochastic thermo, the key connection comes now with the local detail balance. I'm going to claim that the log ratio of forward and backward rate needs to be the change of the internal entropy. So this is summed over y. I can write it in a vectorial way, but explicitly this would be a sum over I. So this is simply the change of entropy. When I do a transition, I will have a change of entropy. That's that part. And minus x E times f. And this explicitly is the sum over y, x, e, y, f, y. And now comes the important interpretation. This is an entropy change in the system well, the rate is when I'm going to multiply by the flux. This is now really the change of entropy when I go from when I go through a transition E, along an edge E. So entropy change in the system. You see that one does not involve the reservoirs. And this with the minus sign is the entropy change in the reservoir. And this is what I was telling you, alluding to before. This is why I assigned to each extensive quantity an intensive field. So whenever I exchange dE with this reservoir and dN, ds will be 1 over t dE minus mu over t dN. So there I use equilibrium thermodynamics because I assume that my reservoirs are very large at equilibrium, and my system, what my system dumps into the reservoirs is only a weak perturbation for the reservoirs. Okay, the system can be far from equilibrium, but the reservoirs, they are large and at equilibrium. And actually, I could argue microscopically that these rates are related to the response properties of the reservoirs. And this is precisely the reason why this property holds. Here I put it as an ansatz, as an assumption. I can justify this microscopically. I mean, for those of you who are familiar with quantum master equation theory, if you do weak coupling theory between the system and the bath, you trace out the bath, you assume they are at equilibrium. These rates are related to the correlation functions of the bath. And because they are at equilibrium, there's this so-called KMS, Kubo-Martin-Schwinger property, that has to do with the time reversal symmetry of this correlation function at equilibrium, and that's what gives these kinds of properties. This is like the microscopic justification. But here I'm claiming that this is the key starting point for stochastic thermodynamics, and you see it makes, I can rationalize this in terms of entropy changes. I wanted to make another comment. What was it? Okay, now it escaped my mind. Yeah, it will come back probably. Good. Okay, so this is the link between physics and stochastic processes that we did until now. Yes?
So we just assume that this holds true.
Yes. I gave you, I mean, we can discuss if you want further the microscopic justifications, but it really comes, it boils down, my statement is, I mean, when I could give an entire lecture on that. It boils down to the fact that, now I remember. It boils down to this KMS condition, the fact that the reservoirs are at equilibrium and that these rates are, they really come from correlation functions of the reservoirs in a linear response theory approach or Fermi golden rule types of rates. And the point I wanted to emphasize is, notice that I make a statement about the ratio of those rates. The rates themselves, I don't make any statements. So the universality is in this forward-backward property, because this is the fact that the bath is at equilibrium that has time reversal symmetry that manifests in that ratio. But the value of the rates themselves can be zillions of things. And I could give you a lot of examples. Maybe this could actually be an exercise where I listed some of the simplest one. You can try, this would be a quantum dot with, no, this is actually a two-level system with the typical spin, typical spin model, spin boson type of rates. They can be derived microscopically. So I have a bath at temperature T. I have a spin at that has two values of the energy, plus delta over 2 minus delta over 2. And the rates, this can be derived microscopically. This is the so-called spectral function of the reservoir, cotangent, hyperbolic. It's to show you that the form can be non-trivial. And so this is the probability to go up, and the probability to go down is and you can check that beta delta. So this is this, right? Because no entropy associated to the states, only energy exchanged. The only field is temperature. So beta is 1 over kBT. Okay, I've tapped beta here, so I leave beta, but beta is 1 over kBT. And you can check that spin rates satisfy this. Another example, you can take Arrhenius rates. Well, let me first do Fermi rates because they are closer to those ones. So this you can check. Fermi rates is the case where you have Fermi reservoirs with a given chemical potential and a temperature, and you take a certain energy level at energy E, or let's call it epsilon, and an electron can hop in or out of the dot, and here the probability, the rate to go, so let me write it in the same way as I did there. So this is if an electron comes in, this is if an electron goes out. So this is going to be proportional to the Fermi distribution at E minus mu. This is going to be proportional to 1 minus the Fermi distribution at E minus mu, because this is the probability to find an electron in the dot and break into the system. This is the probability to take the electron out and find a hole in which you can put the electron. Well, you can check these rates. They satisfy, again, beta epsilon minus mu. You can do the same for Bose rates. If you have epsilon and 0, so it's very similar, but now it's n proportional to n epsilon minus, why do I have minus 1? Yeah, don't put epsilon and W minus is going to be 1 plus and you can check that also here you get e to the minus beta e. Okay, I'm trying to argue these are really, you can, to get those values of the rates, you can write master equation couplings, and I mean a lot is hidden in these coefficients, but it shows you that it always works. And a final one, which is less of a quantum one, but is the Arrhenius rate. Let me do it here. You know that if you have two states separated by a large barrier, my barrier is not that large on my drawing, and that, let's say, this I call epsilon I, epsilon j, and the barrier is Eij star, which is equal to Ji star. So the order of the index doesn't matter for the barrier. This is state I, this is state J. When the noise is weak, so KT is small compared to the height of the barrier. There's the famous theory, Kramers theories. And there are many ways, it goes under many different names. This is the probability to go from J to I. It's proportional to the difference between the barrier and the bottom of the well. And J to I is going to be gamma e to the minus beta, the barrier which does not depend, the energy does not depend on the indexes, EI, because I start from I, so this is now this difference that is relevant. And if you take the ratio, you get minus beta EI minus IJ. Sorry? This gamma? Yeah, this is I didn't give it because for spin boson, it's usually one takes the Druder, but it doesn't depend on the actual form. But a typical one is the Druder rate, the Druder spectral function, which is something like 2. It characterizes the spectral distribution of the bath. But it's a parenthesis, yes. So it's a function of the absolute value of delta. Okay, so this is just a list of examples to motivate. It's not a proof, but I think it's already a certain diversity showing you that I'm not saying nonsense.
Can you please explain why the second submission is about IJ?
Here?
No, that. The second term is the reservoir entropy Y.
Here?
Below that. Now the summation here is sort of ij.
This is Y. Ah, yes, okay, I see the point.
What represents the reservoir in the RMS rate example?
Sorry?
What represents the reservoir in the RMS rate example?
What represents the reservoirs in what example?
The RMS rate.
It's a thermal bath surrounding. This well is in a thermal environment. And so it's a Brownian particle that moves here with KT, and once in a while, with a small probability, that's a weak noise approximation, it can jump to the other side. So it's a reservoir temperature T, exchanging energy. Because if I jump from here to here, that energy had to come from, okay, if you want me to draw the reservoirs, I can draw it here. It's this reservoir that gave the energy to make the transition. Good. Okay, now we did this crucial link. So now we can go back to the mathematical definitions that we had and plug this. Yes.
So, I mean, like in the usual, formulation of stochastic thermodynamics, there, I mean, like one assumes some transition rates and so on, like let's say, which satisfy local detail balance, and then one says that this probability of forward trajectories by time reverse trajectories. So that's, I mean, it looks like this, and but then the entropy is usually log of the probability E of I, right? Which is what you're calling entropy. So that's the one way of looking at it.
Yeah, and you see, for the moment, as I said, this is only the entropy. This object is the change of entropy in the system plus reservoir, only for one transition. Now, of course, I need to put this in my Markov jump process. Okay?
Right here. So for one.
This is for one transition.
So the change in entropy, I mean, in the usual formulation, it would just be log of the probability of I and minus log of.
This is precisely what we're going to do now, because there's going to be the trivial contribution to that, the change of that thing, but also the Shannon part. The Shannon part comes in addition. It's an additional entropic contribution due to the probabilistic nature of the jump process. So this comes really now. So if I didn't answer all your doubt, you tell me again. So, exactly, system entropy. I was careful to say before that Shannon entropy is the object we looked at when we wrote a balance equation for Shannon entropy. Now my claim is that the system entropy, S, is one part that is an obvious trivial one given what I told you. I should maybe have left my drawing. Because to each state I assigned an entropy, right? And so when we have changes along transition, we will have changes of entropy. And so the expectation value of this entropy of every state needs to be there. And then I add the Shannon part, which is pi minus log pi. Okay, so this is. So now I have this little addition because I associated an entropy to the states. Now let's go back to the balance equations. So ds For the balance equation for that one we had already, so I will mostly deal now with the first part. Okay, this is a term that in practice I don't have examples where we deal with it, but you could imagine that if you have an external field, that this entropy of your state might change due to the external field. So that would be that part, plus the sum over I, derivative of pi si, and plus the derivative of the Shannon. I keep it like this for short. So now I'm going to do the trick that I did before. So this one, should I? Yeah, okay. I will rewrite it quickly. So sum over ij, wij, pj, si. Remember, I played that trick already. I put minus sj because this only depends on j. And since it only depends on j, I can act with the sum over I, which is 0. So by adding this, I'm only adding 0. Plus dt Shannon. And this I will now rewrite, let me do it for short here, as 1/2. I also played that game already. wij pj minus wji pi si minus sj. And this I now rewrite as, all this as the 1/2 times the sum over the so both forward and backward epsilon. That's why I still have the 1/2 ge de s. Okay, because this is the flux along every edge. Now I add additional information, which is not really important because the change of entropy does not depend on which edge creates the transition, but I can nonetheless write it like that. And now, if I use, maybe it's a good time to change Blackboard. Sorry? Wait just a sec. Yes? The rate. This is dt. So this is the rate. I erased what I wanted. So it's here. So you remember that we showed that the change, so let me rewrite, dtsi plus now 1/2 sum, which I can remove the 1/2 and now add over positive ones, ge de s. So this is what I had there. And now I use the change of entropy, of Shannon entropy that we had, and we found that it was the entropy production minus the sum over E, Je log We, W minus E. And now we replace this by the local detail balance that we found. And so this will be ds plus xef. And you can already see that this will go away with this. And that I'm left with, let me write it like this, sigma dot plus dt of, I introduce I times f where I is the current exchange with the reservoir. So in vector form, it's like this. You see, it comes from here. So it's JE times this. But I took out the F, so this is simply this times this. And the meaning of that object in component-wise, this depends on y. Okay? Component-wise, this object would be sum over y, Iy times Fy. So this is the change of entropy in the reservoirs. And now, let me reorder it so that we have the final expression. The entropy production is the change of entropy in the system, which is both changes of internal entropy and Shannon, from which, why? I should have, yes, the minus sign comes from the change, because I isolated this. Minus this contribution of entropy, so I'm removing from that change the trivial one that comes from the changes in internal entropy if I have an external time-dependent driving. So that one needs to be there. I mean, again, it's often people ignore simply this term. And then minus I times F. Okay. So you see how crucial it is to know the fluxes of conserved quantity exchanged with the reservoirs to know the entropy production. Actually, if I'm in a non-equilibrium steady state, everything is given by this. So at steady state, and if I don't drive, no time TD is time-dependent driving. The full dissipation is given only by those currents exchanged with the reservoirs, which is something that we also expect from phenomenological thermodynamics. And you see how it's the local detail balance that allows us to make this explicit connection between the expression of entropy production that is really statistical and purely informational in terms of these statistical asymmetry between forward and backward fluxes between edges, and the physics of the problem, which is really how the entropy changes in the system and how it changes in the reservoirs. And this must be always greater or equal than 0. And at the moment, this is why I will go beyond that. Until now, I didn't introduce conservation laws. You already see how physics comes out. But what is still not fully satisfactory is I don't have an immediate understanding of what is my relevant thermodynamic potential, and more importantly, even, what are my thermodynamic forces driving the system? In other words, how should I put my F such that my system will reach equilibrium? At this level is not yet so clear. Yes? This was your confusion? No, sigma dot is 0 at equilibrium. But the point I'm making now is that if you simply look at this, it's not yet immediate to understand what needs to happen physically for your system to be at equilibrium. Okay? I mean, I can anticipate a little to give you a flavor. Imagine that we only have energy exchanges. And imagine that we only have 2 reservoirs. We know that at steady state, I'm simplifying the argument. We will do the general argument next. I know that at steady state, the flux coming out from one reservoir should be equal to the one going in the other, right? At steady state. So in this sum, I will have I and minus I with the different reservoirs, and so I will have a difference of 1 over T. And that's when the temperature gradient appears. But I had to use the fact that I know that energy is conserved. And this is the point. The ingredient missing to really, I think, complete the picture. It's going to be a bit technical, I have to confess, but it's rewarding at the end because it's really a general argument that will allow us to identify the thermodynamic forces driving the system away from equilibrium for any system. And the key is to identify which are the conserved quantities in the system. So that's what I'm going to do next, conservation laws. How much? I still have half an hour? This is a little bit heavy on the linear algebra, but I think, you know, I will write it, I will say what I'm doing. Don't be too worried if you don't understand the details. I mean, myself, whenever I go through that, I need to go back to linear algebra and properties of kernel and images of matrices. So it's not trivial, but the key point is to understand that there's a systematic procedure through which we're going to go through quickly. And at the end, things will become hopefully clear, and we will really identify what is the thermodynamic potential, what are the thermodynamic forces in the system. And because there's exercise afterward, I plan to give you examples of how these general formalisms can be applied in an intuitive way, so in a non-technical way. But I still want to give you the general procedure to show you that it is doable. Okay, for this I need to introduce conservation laws. So I will try to go a bit faster just because, again, I think in any case it's a bit technical, but it's to give you the flavor. I will introduce a matrix M that is the product of matrix X acting on matrix C. Cycles. You see, this is why I wanted to talk about cycle, because that matrix plays an important role. If I write indices here to make it more explicit, this would be a sum over edges y epsilon c epsilon alpha, because the different cycles were labeled by alpha. And what I'm interested in now is to find the left null vectors of M. This is what we call conservation laws. X is my matrix here. It's the changes, it's the one that was giving me the changes of conserved quantity with the different reservoirs. Okay, it's the one that is in the local detail balance, you see? Changes of entropy and the change of conserved quantities along an edge epsilon with a given reservoir rho. Okay, component-wise, just because it makes the indices clear, because there are many indices showing up, y alpha is equal to 0. Okay, so by definition of M, okay, so L T M is X C. This, so C, we said lives in the null space of the incidence matrix, because these were the right null spaces, these were the right null vectors of the incidence matrix. And so if this needs to be equal to 0, it means that these vectors need to be orthogonal to the null space of D, which means that they need to be in the co-image of D. So of D, which is also the row space of D transposed. And this means that to each lambda, to each L lambda, to each conservation law, I can associate a conserved quantity. I will tell you why this is a conserved quantity. That when I apply D transposed on L lambda is equal to X transposed L, because that's the object that lives in the row space of D transposed. Okay, so this, okay, it's linear algebra, but the meaning of that, actually I should have, I will comment on the meaning of that and the meaning of that. This, you can view it in the following way. The matrix M is summing all the change of quantities with reservoirs. You remember Y as the index of a conserved quantity and a given reservoir. So what I'm doing here is I'm taking one conserved quantity and I'm summing its changes along a cycle and looking at how it gets transferred with one reservoir. So if you want a pictorial, you can view it like that. There's a cycle, and I'm going through this cycle, and I'm counting all the changes. Maybe this goes in, this goes out, this goes out, this goes in. All the changes, if it's energy, of energy with the reservoir, this reservoir, when I complete that cycle. That's the meaning of that object. And the meaning of this one is, so L, this is an object living on states. So it's a quantity that I can assign to a state. And it is telling me that when I jump from a state, origin of E, via an edge E, to origin of minus E, I have exchanges. I have changes of L, so L on this and L on this, that I can express in terms of corresponding changes. Now, this guy, where was it? Here. I am summing over all the Y's. So now I'm summing over all Y's, and so meaning all reservoirs and all conserved quantities. So it's a non-trivial linear combination given by these L factors, but such that this combination gives me a change of a quantity that I can assign to an edge. So it's a way to find the quantity that is conserved and that satisfies the balance equation. It's a bit technical and abstract at this point. I can anticipate, in the simplest case, L will end up being the energy, the number of particles. Actually, it will always be, some of the L's will always be what we call the trivial conserved quantities, those that you could have guessed from the beginning, because you know that energy, number of particles need to satisfy conservation laws. However, depending on how your network is structured, you can have additional conservation laws. And so these lambdas, they will tell you that they might be more complicated quantity that involves mixture of number of particles and energies that are also conserved and that will also satisfy balance equation. At this level, it's very abstract, but we will give examples in the exercise to show you how it works. But that's the intuition behind this L. And now, okay, this is again a bit, I can create the matrix of L So I'm basically listing the vectors like this for different lambdas, and here is y. So these are going to be the different lambdas. It's again, this is really linear algebra, and because I want to invert it, it's not a square matrix, so I will create a square matrix that is invertible. Since lambdas are orthogonal vectors in the left null space, I can actually create a square matrix by splitting y. Y was all these guys into a set of y's that I call yp, whose number is equal to lambda, so that is a square matrix, and the yf. It's a way to separate the different y's, okay? Again, it's quite abstract, but this allows me to invert, to have at least an invert in that yp part, and now I can use this on dl. I multiply this by this inverse, the invert of this block, so this is going to be LP, and the invert of that matrix is L minus 1P. So since this is a sum over, I use this now, so I replace DL by this, so XT times L lambda. I split this sum. This is a sum over y. I split it over the p part, the yp part, plus a. And then I multiply by lp minus 1 lambda, so this part will be 1. And then I will have the part with f L p, no, LF. LP minus 1. So you see, these are all matrices that you invert and you multiply. I know it's a bit abstract at this moment, but this allows me to isolate this guy and substitute it in XF. This was the important object, because that guy was the one telling us what is the entropy exchange with the reservoirs. Oh, no, this is the vector. So I can split this in XP, FP, and plus XF, FF. These are vectors. I'm sure I lost most of you here, but just, I'm doing algebra now. I'm substituting this here, and I'm rewriting this as, so this minus this. We will soon get back to the physics. LF, LP minus 1. FP minus FF. Voilà. Okay, and now I already introduced the first important object. You still see there in the back? So these are the non-conservative forces. Non-conservative forces. Okay, I will rewrite it here. So, of course it looks complicated, but what you need to simply keep in mind is that we defined all these objects, right? X was physically defined. From D we could get C. So all these matrices, we know them. M we can get. We can calculate the left null space. So all these objects that are quite complicated, you can get them. There's also non-uniqueness in the sense that I'm using bases. So there's always a freedom in how I choose my bases, not in how many of them there are. So the number of lambda is always fixed. And another crucial point. Yeah, okay, let me finish first. So all these objects are well defined. And now what appears here, okay, there are these matrices that you can think of linear combinations of certain fields yp and certain fields yf. So this is already a notion of differences of fields. And that's why these guys will play the role of forces. It's when these guys will be 0 that the system will be at equilibrium. I'm anticipating a bit, but this is already there. And this is going to be related to the thermodynamic potential, because I'm taking linear combinations with certain set of fields of conserved quantities. And we know also from, if you go from canonical to grand canonical, you add Lagrange multipliers with conserved quantities. These are the analogs of Lagrange multipliers associated to the conserved quantities. So I know it's complicated and it's formal, but I think it's important to show you that there's really a systematic procedure to get there. And I want to also emphasize that this is very important. The number of, you see here I splitted the y's into yp and yf, where yp is the number of lambda. So how many forces I have, this is a vector. So the number of forces is equal to the number of y minus the number of conserved quantities. So I know how many, from the linear algebra, I know how many. These are the number. I construct that matrix. I get the conservation laws. I know how many y's I have. This is the input of my system. And I know already how many forces I will have in my system. So the conservation laws are really crucial to know what are the forces acting on your system. Let's now really average this, because it's going to become more clear. The hard part is, we are over the hard part. This is really, I think, a very important result. I can now, this was xf. I can go back to my local detail balance, log WE, W minus E. This was ds minus xef. So now I use this to write dE. So the D part is this one. I can combine, I can write SI, well, let me do it in vector notation. This minus L, LP minus 1, FP. Okay, this is the first term here. And the second one is the XF along the edges, T times F, the big F, what I call now the big F. And this is what I call now the potential vector. So this guy, its components are on the nodes. So this is the thermodynamic potential that I can now assign to each node. And if I plug this in my entropy balance, so I will use now the one with the Shannon, the first one we derived. Okay, this was what we had. I put this into here. I'm going to get the flux acting on the phi plus the sum over every edge GE x FE times F. And this now I can define as the current exchange with a subset of species that are the, I will call, it's the one associated to the YF. It's a smaller subset than the one that we had initially here. Here we were summing over all the Ys. Here we only sum over a subset that are the YF. This I can rewrite as sum over I time derivative of, we had that object already. So this is only this. And I can further rewrite this object as minus, yeah, because there's a minus here. So, okay, I do it from scratch. dt s Shannon minus the derivative of everything, the expectation value of pi phi I, plus pi parametric derivative. So this is the, if there is driving, how the potential changes, and still the IF F. So this is simple. I'm just substituting, and now I use the fact that for the Shannon, I know that this is the derivative of the Shannon. I could write as such a derivative times log log p. So finally, I can rewrite things like that. IF times the forces plus parametric derivative of the big phi minus total derivative of the big phi, where the big phi is the sum over I pi of phi I plus log pi. And this is my thermodynamic potential. The real one, the averaged one. Okay, so we have the one of the state plus the entropic contribution from the log p part. And this is really the final result I wanted to get at, because now we can show that if f is equal to 0, okay, this term is 0, and as a result of the local detail balance here, this guy is 0. No. I wanted the one written. Okay, here, let me use this one. This is 0, so I have the change of phi I. That's the only part left. So I know that WE divided by W minus E is e to the minus phi origins of minus the edge plus phi origin of the edge. So this is a property of my rate because I put the forces to 0. As a consequence of that, we know that at equilibrium, WE divided by W minus E should be equal to the equilibrium probability at the origins of minus E divided by the probability at the origin of E. And by putting these two things together, you can, this is basic algebra, you eliminate one of the p by summing, you find that pi ek is e to the minus phi I divided by the sum over I e to the minus phi I, which you can also rewrite as E minus phi I minus big phi equilibrium, where the big phi equilibrium is minus the log of the partition function. This you know, this is equilibrium stat mech. Okay, so this is our Gibbs state. So you see, I identified the right thermodynamic potential for my system. Thinking now equilibrium, because I put F to 0. Implicitly what I did in the background is I used the knowledge of conservation law. That knowledge of conservation law allows me to say that if I put those differences of F, linear combination of those F minus those ones, these are related to gradients of intensive quantities. I put them to 0. My system becomes a detail balance system. The local detail balance is this, with the property of equilibrium. The two things together show me that my equilibrium distribution, the one I will reach if I put F to 0, is a Gibbs state with this as the right thermodynamic potential. And I can also prove that the non-equilibrium phi, so the relative, this is basic algebra, very simple, very similar to what we did with the steady state distribution. Since I'm a bit out of time, this is really simple. You can show it. You can do it. This is phi minus phi ek. And the relative entropy, we show that it's always positive. So we can also show that a dynamics where F is equal to 0 and no time-dependent driving, we will have that the entropy production is going to be minus the derivative of phi, which is always positive or equal to 0. And it's also, I can also write this as the derivative of the relative entropy. So again, this is going to be a Lyapunov function. So what my dynamics will do is minimize phi until I reach phi equilibrium. This is, I think, really cool, because this means that I started with this picture, many reservoir exchange various quantities. I showed you a systematic procedure to identify conservation laws. Based on those conservation laws, I know how I need to tune my fields to make the forces vanish. The forces are really, these non-conservative forces are really the thing driving my system away from equilibrium. If I put them to 0, I have a detail balance dynamics, a system that is relaxing to equilibrium. And it's relaxing to equilibrium by minimizing this phi. Of course, if I have forces on, the most common thing that will happen if I wait a long time is that I'm going to reach a non-equilibrium steady state. And in a non-equilibrium steady state, those forces will play a crucial role, and this is what I promised you when I showed you Schnackenberg, which was decomposing the entropy production as a sum of current at steady state. He was decomposing current along cycle plus forces along cycle. I have something that is drastically reduced, and that is a sum, in most cases, is a sum of the fundamental forces times a subset of currents exchanged with the reservoir. I don't need them all. I just erased the fact that the number of F is the number of Y minus the number of conservation laws. You may think initially that you need all of the fluxes exchanged with the reservoir. No. If you have conservation law, it allows you to reduce and get only a subset of them that fixes the forces. These are really the key objects to understand when your system is driven out of equilibrium. Finally, quasi-reversible transformation, very quickly. this is, I need F equal to 0, but I drive my system. I was planning to show you this, but I leave this as an exercise. A quasi-static transformation is very slow, so that the relaxation time of your system is fast compared to the driving time scale, meaning that Pi is going to be pretty close to Pi ek plus a little deviation. Substitute this in the entropy production. Convince yourself that the entropy production is going to be of order dp squared. So this is of order dp squared. This is 0. This is of order dp. This is of order dp. So for a quasi-static transformation, I get that this is equal to this. And this will be the equilibrium one. Okay? So I recover also these things, because this, in simplest case of energy being driven, this would be the work a la Jarzynski. You would find that the work in the reversible case is equal to the change of free energy. This is a very special case, but here you recover it in general. So I know it was a bit tough, but I think it was worth it because of the general picture that it gives you. You know, it's again the key message. You start with this picture of many reservoirs exchanging stuff with your system. You construct these matrices. You find the conservation laws. Based on those conservation laws, you can identify what are the fundamental, the non-conservative forces that are the fundamental object driving your system away from equilibrium, and what is the thermodynamic potential governing your system. So I think this is really cool, although abstract, and I will use the exercise session to give a few really simple illustrations where you will say, ah, you could have said it earlier. Because in some simple examples, yes, you will understand what are those balance equations. They are pretty obvious. But actually, the reason how we got there is chemistry. In chemistry, I challenge you to find conservation laws easily, because chemistry has highly non-trivial conservation laws, and you really need to go via this systematic procedure to find them. I think this is the most difficult case where the systematic procedure is really needed. In some simple case, sometimes you don't need to go through the complicated procedure. You can do it by hand. And that's what I want to show you next in the exercise session. But I hope that the big picture now is clear. And I think the central achievement is really this one, where we have a very systematic procedure to identify potential and forces. I should add that it's not unique. You can because this set of reference F versus force F is, you have some freedom. It's the same freedom that you have when you define a gradient. You can take one bath as a reference and define the difference between the number 2 and versus number 1, or number 1 versus number 2. It's the same kind of thing, but the number of forces that you have is unique. So the sum of these guys is unique, but the decomposition is not unique. I hope I didn't kill you all.
So I have a question. So like if I am trying to understand some chemical reactions and all, so how does this actually, how is this going to help me in the understanding?
Well, you know, if you have, if I give you a box of chemical reactions, and some of these species are in very high abundance, that's how you drive the system away from equilibrium. By putting high abundances is like fixing chemical potential of those species. And you want to know, is this system going to be out of equilibrium or not? Is it going to relax to equilibrium, or are there going to be fluxes between those concentrations that I hold fixed? You need to make this analysis and to find out whether there are forces in your systems. And if there are, most likely, when they are non-zero, you will have, the system will be far from equilibrium. There will be fluxes through the system. If you set them to 0, that's a way to have an open system at equilibrium because you tune the fields, the intensive field, in such a way that there's no driving force acting on your system. This is the analog in the simplest case of setting a thermal gradients to 0. You can have two baths, right? As long as the temperatures are different, you're going to be out of equilibrium. If you set them equal, then you are at equilibrium. That's the simplest case because you have one conservation law, only two baths. This is the generalization. I have arbitrary number of baths with many different intensive fields. When is my system at equilibrium? Is when I choose a very special set of values for these intensive fields such that these forces are 0. Then my system is at equilibrium. If it's not, then there will be fluxes circulating in my system. And how many of them do I need to know the dissipation? I erased it again. Number of y minus number of conservation laws.
Okay, so I can calculate the net dissipation going on in a reaction. Is that
Okay, maybe a practical application. I give you a system, and I connect many reservoirs to that system. Okay.
So these are reservoirs of chemicals.
It could be anything, right? Because for chemicals, it would be, chemical potential of species A, species B. These are involved in different reactions here. Now, first question, how do I need to choose my chemical potentials to be at equilibrium? Well, you need to find the F in terms of these mu's and put those F to 0. So there's a special choice of these mu's such that your system is at equilibrium and all the fluxes will be 0. What if you're not there? In that case, there's going to be, let's say, if I have two forces, I don't need to know this current and this current. Only by knowing this current and this current, I can have the exact dissipation in my system. Because they are considered at steady state, because I'm assuming I'm at steady state now. Because they are conservation laws such that this and this determines this and this. So I can tell the experimentalists, you need to only measure these two things, and you will capture the full dissipation in the system. So there's actually an interesting way to look at it. We started with entropy production that is a sum over every flux along every edge. Okay? Then let's say steady state to make it simple. Then we went to cycles. I told you you can actually reduce this in terms of cycles. Then now what I'm telling you, I showed you that you can go from cycle to all the reservoirs, all of them. And now I tell you, with conservation law, you can further reduce to a subset of reservoirs because they are conservation laws. So the knowledge that you need to reconstruct the dissipation has been drastically reduced. And instead of having to monitor every step into your system along every edge, you only need to monitor these physical fluxes with a subset of reservoirs. That's one way to. But you also, it's also very nice to see that what the dynamics with F equal to 0 is doing is actually extremizing the right thermodynamic potential. You know, when you go from canonical to grand canonical, you add mu n to your to the probability distribution. And that becomes the right thermodynamic potential to describe that situation at equilibrium. Here, this phi is doing precisely this, you see? This phi, in the simplest case that I said going from canonical to grand canonical, it would be mu n. But now I'm taking, if there are more complex conservation laws, I'm taking certain combination of fields times conservation laws. So, you know, a mu n1, mu n2. It's like I add these Lagrange multipliers and conserve quantity that is exchanged with the environment. And I show that, I mean, I could do by hand. I could say at equilibrium, my system extremizes this potential. And this is true. But I don't even need to do it because the dynamics does it for me. The dynamics is actually extremizing or minimizing this potential. So I have a dynamical realization of the max-nth principle, if you want, because the max-nth prescription would be choose your right Lagrange multiplier, maximize your entropy by fixing this Lagrange multiplier, equilibrium is the maximum. I don't need to do that. The dynamics does it for me in the special case where f is equal to 0. So I really have two key objects, phi and f, that are produced by the theory. And that crucially depend on conservation law. So conservation law really play a crucial role in non-equilibrium systems to identify the forces and the potential ruling the dissipation.
So you have this system and when you wrote down, right? You have this EI, SI, and then you have this Shannon part.
Yeah.
Right? So usually, like when you write down the path, you only have the system entropy, the Shannon part, right? So the system part is the part basically which other degrees of freedom which is not accounted by the Shannon
Yeah.
part.
Yeah. The example, the best, I think, the best example for physicists is the Potts model. If you go, if instead of describing the all microscopic configuration, you work at the level where you work with density, you know that your density have an internal, a given value of the occupation number has an entropy because there are many microscopic configuration corresponding to that density. And so you need to assign an entropy that is log of the complexion number of states corresponding to that density. And that would be that I would be the occupation vector, and SI, the entropy, which is log of the complexion number of that state I.
Like, for example, if I look at in the continuum algebra equation,
Mm-hmm.
right? See, I can either look at in the underdamped picture where I have both velocity and the position. But suppose I just look at only the overdamped one where I only have the position.
Yes.
This extra part will basically will this give me the contribution from this velocity.
Yes. Yes.
Right, which is not there in my
Yes.
log of dx.
Yes. And this links a bit back to your original question, because this is an example where we know that if you are non-isothermal, you're running in trouble, because your velocity, instead of going to an equilibrium, goes to a non-equilibrium state, and then you cannot do that because you're dissipating in the degree of freedom that you eliminated. So that's precisely an example where you cannot apply naively stochastic thermodynamics, I mean, overdamped stochastic thermodynamics for non-isothermal system, because momentum is not equilibrating, is actually relaxing to a non-equilibrium steady state. But if temperature is the same, then it's fine. It equilibrates, you eliminate it, and you can assign an entropy to that state.
Far down to that entropy, right? I might have a lot of other degrees of freedom I may not even know, right?
Yes.
In my model. And that will keep on increasing my
Yeah.
that part.
You know, at the end, the question that is relevant is whether or not this entropy will change in the processes that you're interested in. If it, most of the time there is entropy below, but you don't care about it because there are no changes of that entropy. For chemistry is another example where it cares, because when you have a chemical reaction, you start from, let's say, a molecule that breaks in two. The initial molecule has a given free energy, so energy, enthalpy, and entropy. The reaction takes it apart into two pieces, which each have an entropy, but the entropy change between the initial molecule and the sum of the final molecule. So the change of entropy there needs to be taken into account. If you have a breaking process where the entropy doesn't change, then you don't care. You can ignore that part. And actually, in many applications, you can ignore that part. But POTS and chemistry are two examples where you cannot. Yeah, yeah.
Start at 5 or something, is that like maybe because it's already 4:20?
Yeah, okay.
Maybe
Yeah, 5 is.
so there is a tutorial which we can start at maybe 5. Right? There's only one lecturer, so Maximilian will be present. So from 5 to 6 the tutorial. And so tomorrow there is a bank fair, and the 2:30 to 4 there's a tutorial, but we thought we'll convert it into a sort of introduction session. So maybe you can just say something about yourself. And actually we sent you a mail. You can send us just one slide which maybe just summarizes where you are from and what you do. Then it will be easy to, we'll just flash it and you can just talk about it. So that might be an efficient way to just go through the introduction. So please send us a slide by today, tonight.
I mean, who you are means what you do, basically.
What, yeah. Yeah,